We take it for granted that our computers, which are really just a bunch of on-off switches, can do all this complex math. But have you ever really stopped to wonder how? How do those ones and zeros actually add up to anything? Well, today we're going to pull back the curtain on that little piece of magic. So that's the big question, right? How in the world does a machine that only gets on and off add two numbers together? It sounds kind of impossible, doesn't it? Well, the solution is actually super elegant, and it all starts with one very simple little circuit. All right, so our story begins with the most basic building block of all computer math, something called the half adder. You can think of this as like the very first math lesson we give to a machine. It's simple, but it is absolutely fundamental. So what is a half adder? Well, it's a tiny circuit designed to do just one job: add two single bits together. That's it. It takes in two things, let's call them A and B, and it spits out two answers: the sum, which is, the result, and a carry. And that carry output, that's the key to, well, everything that comes next.
Okay, so this table shows us every possible thing that can happen. 0 plus 0, the sum is 0, and there's nothing to carry over. Simple. 0 plus 1 is 1, and again, no carry. Same for 1 plus 0. But look at that last line. This is where it gets interesting. 1 plus 1. In binary, the number 2 is written as 1, 0. So the sum is 0, and the carry output flips to 1. It's the circuit's way of saying, hey, the answer is 2.
The half adder seems pretty clever, right? I mean, it can do basic addition, but the moment we try to do anything just a little more complicated, we smack right into a wall. It has this one critical built-in flaw that just stops it from doing any real-world math.
Let's make this real for a second. What happens when you're adding bigger numbers? Like in binary, adding 3, which is 11, and 1, which is 0, 1. You've got to have a way to handle the answer from the first column and carry it over to the next one.
And this probably takes you way back. Remember in grade school, carrying the 1? You add 9 and 5, you write down the 4, and you carry that little 1 over to the next column. Well, computers have to do the exact same thing, just with ones and zeros. And here's the fatal flaw. The half adder has no way to accept a number being carried in from the last step. It's got two inputs, A and B, but there's no third slot for a carry in. And that limitation means you can't chain them together to add bigger numbers. It's a dead end. But don't worry, because every good story needs a hero. And in the story of digital logic, our hero is the full adder. This is the brilliant little circuit that solves that pesky carry problem and really unlocks the true power of computation. Okay, so a full adder is a lot like a half adder, but with one crucial upgrade. It adds 3 bits, our two inputs, A and B, plus a third input called the carry in, or sin. That third input is the game changer. It's the slot for the number we carried over from the last column. And what's so beautiful about this is how simple ideas build on each other. You see, a full adder is actually just built from 2 of the half adders we just talked about, connected with a single little logic gate. The first half adder adds A and B, and the second one adds that result to whatever came in on the carry-in. It's just a perfect example of using a simple block to build something way more powerful. So now, let's zoom out and see how this all comes together. The full adder isn't just a cool trick. It is one of the most important little pieces in all of digital electronics. This simple idea, a circuit that can add 3 single bits, is the foundation for how every single computer, phone, and calculator does math. Let's put them side by side. The half adder? 2 inputs. The full adder? 3. The half adder can't be chained, but the full adder, it can be cascaded, which just means linked together, to add numbers of any size you want. And that ability to be chained is exactly why the full adder is the fundamental piece inside every computer's Arithmetic Logic Unit, or ALU. That's basically the math department of the processor. And when I say you'll find full adders everywhere, I mean everywhere. They are at the very heart of your computer's CPU and your graphics card's GPU. They power every single calculator. They're even used for way more complex stuff like multiplication and figuring out memory addresses so your computer knows where to find its data. This little circuit is a total workhorse. The source material really hits the nail on the head here. It says full adders are the essential building blocks for performing arithmetic in a computer's CPU. They're not just some interesting theory. Without them, the entire digital world as we know it just couldn't do its most basic job. So, the next time you use a calculator or play a video game, you'll know that deep down inside, billions of tiny full adders are linked together, just carrying the one over and over again at unbelievable speeds. And it kind of leaves you with one last thought. If a circuit this simple is the engine for all computer math, what other brilliant, simple ideas are hiding in plain sight, powering the rest of our digital world?